Hey, if you haven't already, go ahead and make a new section in your notebook for waves. We are starting with some new information. If you don't have the tabs today, that's totally fine. Just leave about a page or two and then start in with the notes over this wave section, and we'll make the tabs when I get back. In this section, we're going to talk all about waves. We'll be covering just general characteristics of waves. We'll talk about sound waves specifically, and music and how sound wave behavior influences music and sounds. Light and the electromagnetic spectrum, anything from X-rays to gamma rays to microwaves, and how they behave. And we'll talk about general wave behaviors like reflection and bending. And then we'll finish up with lenses and mirrors and how light and other types of waves behave when they encounter these special types of objects. So we're going to start today with just general characteristics of waves and what is a wave and what are the parts of a wave. So first off, what is a wave? No matter what kind of wave we're talking about, whether it's an X-ray or a sound wave or a tsunami wave like you see in the picture here, a wave is a rhythmic disturbance that carries energy from one place to another. Your energy is moving. It could be energy moving from an earthquake through a tsunami. It could be sound moving from my voice to the camera here and picking it up and then transferring to your ears from the headphones that you're wearing. But it's carrying energy from one place to another with some kind of a rhythmic disturbance. We can categorize waves based on what kind of material they need to move through, or actually whether they need a material at all. Mechanical waves have to have some kind of a material to go through. Think about taking like a rope and flicking the rope, and you see the little wave moving down the length of the rope. When you get to the end of the rope, the wave stops. It doesn't move just out into, nothingness. It stops with the end of the rope. That's a mechanical wave. It has to have some kind of material to move through. The other option is an electromagnetic wave. Electromagnetic waves can move on their own because of the way they're set up. You see electro and you see magnetic. Remember we talked about electricity and magnetism when we just finished up, and how you can use electricity to create magnets. We call them electromagnets or solenoids. And you can use magnets to create electricity, which is how we got into the generators and the turbines, and how you spin that coil of wire in the magnetic field and push electricity through our current. And so the two are very integrally connected. And we see that with these electromagnetic waves. You have an electric field vibrating one direction, and you have a magnetic field vibrating perpendicular to that, and they pull off of each other. It's almost like they're held together and vibrate perpendicular to each other. And because they're vibrating off of each other, they don't need a material to go through. They can go through empty space. So think about light and UV radiation and gamma rays coming from the sun to the earth. There's nothing between us and the sun, and so it can move without having some kind of a material, air or ground or whatnot to move through. We can further classify types of waves based on how they move. Transverse waves vibrate perpendicular to the direction that the wave is moving. So you see actually the second picture, I have them out of order. The second picture is transverse. You see the person holding the string and wiggling the string. The wiggle is up and down, but the wave is being sent down the length of the string. So that vibration is perpendicular to the way that the wave is moving. In contrast, the top picture is a longitudinal wave. It's kind of like a slinky. If you take a slinky and shake it back and forth, that wave is going in the same direction that the particles are vibrating. It's vibrating this way and it's transferring this way. So that's a longitudinal wave. Long ways, I was always thinking longitudinal. It's going lengthwise, down the length of the wave. And then surface waves like earthquake waves, waves on the beach, waves in the ocean, those waves have a little bit of characteristic of both. You get more of a rolling motion like we see here. You have a little bit of a push-pull, but you also have an up and down motion as well. If you've ever been on a boat when the waves are rocking or floated in the ocean down at the beach, you can kind of feel that more of a circular motion than just moving back and forth or moving straight up and down. It's that circular that we see here in the picture there. All right, so we're going to do some drawing and labeling. We're going to draw and label some transverse waves and some longitudinal waves. And then the parts that we label, you'll go back in a little bit and define a little bit more fully. We're just going to kind of label the parts here. The first one that we see here is a transverse wave. I'm just going to draw squiggles up and down. There you go. Doesn't have to be anything really fancy. In the middle, you see that line there? That line, I'm going to draw mine dotted because there's not really a wave or a part of the wave there. What that line in the middle represents is where our material would be if there were no energy. So think about, like we talked about, the jump rope or a rope that you come and flick. If we're not flicking the rope, then it's just here, still, in the middle, no energy. But when we put energy into the rope, then it deviates from that middle, that line of equilibrium, and gets higher or gets lower. So a couple of ones here you see, number one is connecting this top part to that top part. We could also connect two bottom points. It's the same. This length between two similar points is called the wavelength. So I'm going to write in here wavelength. Okay, wavelength, two similar points on a wave. It could be the top to the top, it could be the bottom to the bottom. Be careful doing middle to middle because you don't want to do this part right here in the middle. That's only half of the wavelength. You want to do from the part where it's going down to the next part where it's going down, or where it's going up to where it's going up. Don't just do the length of the middle. Okay, so that's wavelength. You see number two here on our diagram is from that middle point, that line of equilibrium, up. You could also do from that line of equilibrium down. Either way, it's how far you're deviating from having no energy, and that's called the amplitude. A-M-P-L-I-T-U-D-E, amplitude. Okay. Finally, 3 and 4 are pointing to the top and the bottom. The top is called the crest. The bottom is called the trough. T-R-O-U-G-H, trough. Okay. Crest on the top, trough on the bottom. Crest, a couple ways to remember that. Some people like to use the word crust, like the top of their bread, the outer layer of the earth, and kind of equate crest and crust together. Trough, if you look, it kind of looks like a bucket that you could put food in or put water in to feed your animals. So a watering trough, that's this part right here. This bottom part looks like you could fill it with water. It would hold. It's like a little bucket. So trough is the bottom part, crest is the top part. Okay? With longitudinal waves, it gets a little bit different. We still have the wave moving, and we still have an amount of energy that's being transferred, but there's no highs and lows. What we have here, which we're drawing, this is more like a slinky. You could do it two ways. I'm going to do mine kind of like we have on the picture there. We have it really squished up, and then you have it spread out. Okay, really squished up and then spread out, kind of like on the picture. If you prefer, you could do molecules, have your molecules really close together, and then your molecules spread out, and then your molecules really close together, and then your molecules spread out. That's fine too, however you prefer it. With this, you still get a wavelength and an amplitude, but it's a little different. It looks a little different. Your wavelength is from your squishy part to the next squishy part. So like from here to here, where it's squished together really tight, or here where it's very dense to the next part where it's very dense. I'm just going to put WL because we've already written wavelength once, but there's our wavelength. Okay, the length of the wave from one part to the next similar part. Amplitude is, I would say, how densely it is compacted. So the amplitude would be like how dense it is here, or how dense it is here. Okay, that would be your amplitude, is how squished or how spread out your wave is from not being squished at all. If you just had a slinky laying on a table and you didn't wiggle it, then it would just all be spread evenly. But when we come back and give it a shake, then you get these parts that are compressed and parts that are not as compressed. So it's how much energy you give it determines how compressed those compressions are. So the parts that are compressed together, okay, either here or here, wherever you see it like densely compacted, those are called compressions. Okay, and if you're missing my writing, it'll be on the next slide, just wait. Okay, compressions are the squishy together part. The spread apart parts, the ones that are farther apart, are called rarefactions. So R-A-R-E faction, F-A-C-T-I-O-N. Okay, rarefaction. Okay, rarefaction is the spread out portion. It's rare to come across one. They're spread out. Okay. So now we'll kind of define it a little closer. We wrote amplitude on there, both under a transverse wave and under a longitudinal wave. For both of those, your amplitude is your displacement from rest, if you had no energy. More work that we do, the more energy that we put into that wave, the larger the amplitude that we get, the more you deviate from your line of equilibrium where you have no energy. Your wavelength is that distance from one point to another, from crest to crest or from trough to trough. One thing I put down here is we represent that with the Greek letter gamma. It's a little upside down Y. So if you see that, like in this picture here, they have wavelength and then they have your little Greek letter, then that is your symbol, and that'll kind of help us out when we want to shorthand it. Okay. On your compressions, there we kind of drew what we did a little second ago, wavelength from compression to compression, and then your amplitude would be that line density, how dense your line is. All right, something that you really can't draw is the time period. The period is the time that it takes for one wavelength to go past. We represent that with a big T instead of little t for time like we've been doing, because your big T is a repetitive event. It's not how long the wave is moving, because if we measured that, then it would be an infinite amount of time for ocean waves, but how long it takes for one wave to go by. Many waves go by, but the time period would be how long it takes for one complete wave to go by. And we usually measure that in seconds, just like we do time. Frequency is related to time, but it's how many oscillations, how many wavelengths go by in 1 second. So your frequency and your time period are actually inverses of each other. You see that F equals 1 over T over there. Your frequency is the inverse of your time period. So let's say if you look down at the bottom wave down there where it says 3 hertz, okay, frequency is measured in hertz. If you look, then they've marked the side 1 second. In 1 second, you have 3 complete waves that are going by. So your frequency is 3 hertz. How long would the time period be? How long would it take for just one wave to go by? Well, it'd be 1/3 of a second. So if your frequency is 3, your time period is 1/3. It only takes 1/3 of a second for one to go by because you can fit 3 into 1 second. They're inversely related. All right, and finally speed. The speed of the wave depends on the material that you're going through. Speed is calculated by using frequency times the wavelength. There's that formula down there. Make sure you write that where you can get to it when we start doing practice problems. So speed is frequency times the wavelength. And it depends on the material. Say like sound. Sound will travel faster when you have more densely compacted materials like solids, and will travel slower. In fact, it will not travel at all where you have no material. Like say in outer space, you have the whole movie tagline, "In space, no one can hear you scream," because sound does not move at all where you have no material for it to go through. And we'll talk about that more when we talk deeper into sound and its properties. But the speed of the sound, the speed of the light, the speed of the X-ray, whatever we're working with, does depend on what it's moving through. Okay, and that's how it's calculated. So that's going to stop us here with general waves, wave information, wave behaviors. We'll pick up next time specifically about sound and longitudinal waves and how they behave and how they make music for us.